Hi, everyone. As you can read, I'm David. So I want to talk to you a little bit about one way to do some recycling. So just like if you go buy some beer, it comes in an aluminum can, right? And someone had to go dig up the aluminum, and like in programming languages, that's kind of like you sit down with like your paper and you figure out like what's my programming language going to do? How's it going to work? How am I going to encode things in it? And then the aluminum goes from the mine up into the smelter, and they refine it and make this block of fairly pure aluminum. And that's kind of like where you sit down and you like figure out the math. Like, do I have type safety? Maybe you don't do this, but you should. If you don't, feel guilty. Yeah. And then after that, you've got to communicate your language, right? You've got to tell people like you did all this math, but there's no point to doing all the math without having without telling anybody that you did it. It's like a doomsday weapon. And this is, maybe kind of like where you take your block of aluminum, and I don't actually know how to make a can. I should have looked this up. But you squish it into a can shape. Let's assume there's a big can press that makes cans. I don't know. Right? And then then you take your can and you put beer in it. And, I think putting beer in things is a bit like implementing a programming language in that it's best done late at night. But then once you've implemented your language, then in order to know if it really works, then you should actually like sit down and maybe use it a little bit. Like give it to some users, see like, can you actually solve the things you want to solve? And just like your empty beer can should really go back and get melted into new beer cans. Like you're going to take that input and put it back into your language design, and you actually end up wanting to go around the loop a whole bunch of times. We're recycling ideas each time, making them a little bit different. But largely this, yeah. And so I'm going to talk to you about one sort of way you might do that and get some feedback. So for those who don't know me, right now I'm working at Dion Digital with I got two of my colleagues over here. We've got a declarative DSL for specifying contracts and various tools and things connected to that. Before that, I worked at Galwa in Portland, Oregon on verification tools, some like high assurance binary format processing stuff, and also a bit of election security. That was super fun. I wrote The Little Typer with Dan Friedman before that while I was a postdoc at Indiana University working on Racket and trying to like run a proof assistant in Racket's macro expander. That never really worked, but it was really fun. I used to have a podcast. It's sort of indefinite leave right now because I've got a kid, and the other two people I made it with, one of them is just starting a postdoc, and he had to write his thesis, and the other one didn't want to do type theory anymore, but it was fun. And then I've gotten a PhD from ITU back in 2016 in this lovely city. I came back in January. And then I used to work on Idris, which is this dependent type programming language, just so you all know a little bit where I'm from. So the agenda for tonight, first off, I'm going to give you a quick demo of some things and then show you a stripped down version of our DSL, really tiny with all the important things removed, because I think that that's a suitable size to do a quick demo. And then show how to model that in PLT Redex, which is a tool developed by Robbie Findler and collaborators to make this exact process go faster. And then after that, I want to show you a thing that I learned from David Van Horn, which is how you take your model in Redex and actually turn it into a somewhat usable implementation. So you can do that crucial step of sitting down and using it to encode things and see if it actually is convenient and ergonomic for those purposes. And then if we have any time at the end, I can show you how to make figures for your papers. So I'm going to assume that you know something about the things on the screen right now. So that like if I show you a grammar in BNF, that it won't be the first time you've seen one. If so, just please ask, and I'll try to answer things at a suitable abstraction level. That you've seen some typing rules, with like the horizontal line with the premises up top and the conclusion on the bottom. That you've seen operational semantics before, and maybe also used a parser generator like yak, happy, or menhir. You can see what part of the world I like to hang out in here, and maybe also that parentheses don't scare you all that much. So when we're describing a language, we usually use a set of formal tools that the community has in common. Right, so we've got a grammar, so we might have a grammar, we say like a contract is either trivially successful or absolutely broken and unsatisfiable, or like we're gonna do a thing and then continue as this other one, or maybe we're gonna do two at once, and there could be a bunch of those productions, right? We also have some typing rules, where we might say that if we want to apply some expression E1 to E2, then E1 had better have a function type, and E2 had better be a suitable argument for that. And then we also might say that beta reduction is a thing we do. And so Redex really is a tool for taking these descriptions and then getting you a whole bunch of other useful stuff out of them. In addition, I'll sit down so you can see past me. Was that a question? No. Okay. I see hands coming up, and I'm like, question, but yeah. So it gives you the ability to experiment with your definition, to take an expression and say like, well, if I repeatedly apply these reduction rules, what do I get? And have the computer do it instead of having to do it yourself. It can give you some like random testing, like QuickCheck-style. It can help you visualize things a little bit, and it can make figures for your paper so that you don't introduce typos in the process of transcribing to LaTeX. If you think this sounds fun, then I recommend you go find Robbie Findler's talk from Popple on Redex a few years ago, where he basically shows a bunch of unimportant but nonetheless confusing bugs in papers. In other words, he took a bunch of published results, and then they essentially implemented them all in Redex and just found tons of little mistakes. Like, maybe there was a subscript 1 where there should have been a subscript 2, those kind of things. And it slipped by everyone who tried to review it, but a machine would have caught it. And these kinds of things are fine if you're trained, but they make the paper much less useful for like new students and people who are having a harder time figuring them out. And it's better if we don't have them. So it's nice to have a tool for working on that. Right. So we're going to be working with this little language here. Yeah, there's a lot on the slide here. Okay, see what I mean? Like it gets hard to like internalize all this just by looking at it. But we've got contracts, so those are success or failure, or we've got disjunction of contracts, which says you can do the thing in C1 or the thing in C2. We've got conjunction, which says you got to do both, and then we've got this thing where we've got some variable x, and then we're saying that a thing is going to happen, and that thing has type tau, and then it had better satisfy p, which is going to be a Boolean expression, which is allowed to refer to x, and then we'll continue as that other embedded C. We can also have a little expression language here, so that consists of variables, Booleans, like true and false, numbers, unary operators applied to expressions, binary operators between expressions, agents, or payments, which is the only event we have in this little tiny world. Then we've got the agents. There's only 4 of them. They're named Alice, Bob, Carol, and Donovan, because that's what we call people. And the unary operators are like 2 kinds of negation. So you've got like unary minus, not, and then projections out of that payment type. And then the binary operations are sort of your usual arithmetic operators, comparisons, and conjunction and disjunction. Right. So now we got some types too, right? It's like we want to have rules for adding types to things. Oh, this font is getting small. How am I ever going to know that what I'm doing is right? Let's see. So I get my typing contexts. Those are either the empty context or some gamma followed by x with type t, where t is either our event types. In this case, that was just payment, but I've architected this to be extensible in the future. We've also got numbers, Booleans, and agents. A selection of some of the rules we might have are that, variables, we find their types by looking it up in the context. Boolean literals are just Booleans. Payments, we have to have the appropriate types for each of the fields inside of it. And then I've got this idea of a thing being a contract, which is to say it's well-formed. Most of the contracts do that the way you'd expect. And then we can see that the one that awaits an event and checks it inserts the event into the context so that the expression and the continuing contract can talk about it. All right, you still with me? Let's do some operational semantics for this thing. All right, so we define a notion of values, and then we define evaluation context because I spent time at Indiana. So the idea of this evaluation context is that we're providing a grammar in which all of the boring reductions can happen, and then we'll give reduction rules just for the interesting computational bits where cool things happen, right? So you can think of E as being a little bit like a zipper into expressions, with the exception that it encodes an evaluation strategy by determining that certain subpositions must be values, right? So we can see that our payment constructor is evaluated from left to right, for example. And that binary operators we evaluate on the left and then on the right. And the two brackets together is the whole where interesting evaluation can happen. Okay, what's the interesting evaluation? Oh, here's some rules. Okay, let's not do any of that. This is completely overwhelming. I don't want anything to do with it. Instead, I want the computer to help me, because sitting down and writing all this stuff by hand is error-prone and complicated. It's tedious for people who are made right in the head. I don't actually find it that tedious, but yeah. All right. So I am going to do a quick little introduction to Redex, and then I'll show you how the language in the slide looked. But I'm going to start with a language that we all know a little bit better. So has anyone in here never used Racket before? Okay, so most of you have tried it, so that's a good sign. Please, if there's any syntactic thing that is confusing, just shout out a question. I do well being interrupted. So the first thing I'm going to do is I'm going to import Redex. It's an embedded DSL, so it takes the form of a library. And I'm going to define a language. And I'm going to call this language lambda calculus, so I'll call that LC. And LC has the first production that we have, the first non-terminal is going to be called E for expression. And expressions can either be, let's add numbers to our lambda calculus just to make it a little more fun. Number here is a thing built into Redex. It comes with a set of non-terminals you can use if you want to, like numbers and booleans and strings and those sorts of things. And then we're going to have two expressions, and that's a function application. And we'll have lambda x e, and we're going to have x. Right, so if I put these all on their own lines, then maybe it becomes easier to read. So what I'm saying here is that I've got a non-terminal e, and here, so Redex has a built-in notion of pattern matching, where the names of things tell you what syntactic category they come from. So when I say E1, E2 here, I'm saying two things of syntactic category E that don't have to be the same. And
line breaks just either.
So actually, it's just I can put as many I can put as many productions after the colon equal as I want, and line break or space or whatever I want to put between them.
You said they don't have to be the same, but they can be the same.
Yes.
Okay.
Yeah. I could write 5 applied to 5 if I wanted to.
And is X and E, that's different? It knows that's different, one survival and...
So right now, it doesn't know what X means, actually.
Okay.
So I'm going to define X, and this is the most wonderfully named operator in all of Redex, I think, called variable not otherwise mentioned. And so variable not otherwise mentioned says that any identifier that does not occur as a terminal or a non-terminal is a valid, it will match that pattern, right? So basically means all the other symbols. That's pretty handy. So, and I haven't quite specified the syntax of lambda calculus yet, because I also need to say that this X right here is bound in this context E right here. So I can say binding forms, and then I can start listing those out. So I'll say lambda X, E, and then that refers to X. And there's a fairly complicated language for describing these binding forms, which can get you to like mediumly complicated stuff. Otherwise, you end up having to write alpha equivalence and substitution by hand, which isn't the end of the world, it's just kind of tedious. Did I answer your question? Everyone? Yeah, okay.
Just a comment. Why
Yeah.
is this a strike through MC at the top?
So that's my Emacs mode. It puts a strike through anything I define that I don't reference. Like it's an unused definition warning, basically. So once I do something with this language, I'll see that'll go away. It also does all sorts of nice like highlighting. Yeah. Okay. So now I have defined this language LC. What can I do with it? Well, like I could certainly try to write programs in it, but I might also have a deadline, and so then I want to say, you know, let render language LC, and then I get this little tiny picture right here. It's a little bit bigger. And so, you know, this isn't the most beautiful of renderings, but there are some things I can go into. If we have time at the end, I'll show you how they work, where you can, you know, replace the lambda with a lambda and get rid of the parentheses around it and pretty print things and make them look good. It's a little bit clunky, but it's not the worst in the world. Okay. So, but a language is more than its syntax, right? Like we also need its semantics. So I'm going to go in and first attach some static semantics to this thing. I'm going to give it some types. And so I'm going to say that variables bound by a lambda have to be type annotated. And now I have to say what the types are. So the types will consist of num or arrow TT. And there's nothing that says I have to put the arrow first. I'm just an inveterate Lisper, and so that's what I'm going to do. It would be just as valid here to write it like that. And now I can define my type system. So I could say define judgment form, and then I'm going to be in the language LC, and now that crossed out line goes away. And now a judgment form I have to give a mode to, which I'll explain in a bit. Actually, I'll explain it once I write it. So I can say mode, and then that's going to be, I first name my form of judgment, so I'll call it has type. And then I have to give whether or not I expect Redex to be able to invent things in each position, or whether or not I will provide them and just have it check that I did it right. And in the case of simply typed lambda calculus, I've got my context coming in, and I've got my expression coming in, and it should be able to find the type for me. So I'll say that the mode is in, out.
I don't get that. What is has type?
Has type is the name of the form of judgment I'm defining right now. So I'll actually need to come back, and because I forgot to define something here, I'll say, oh, so that gamma will consist of either a dot or an extension of a gamma with some x and some t. So this is what we would write in normal notation as something like that. Might as well leave that around. Okay. And so then I can say that one thing I might want to do is find the type of a number. So I write myself a horizontal line, and then I say has type in all gammas, a thing that matches the production number has this type num. And now I've already got some code that I can actually use for something, right? So I can pop over here, and I can say render judgment form has type, and we see a certain representation of the typing rule. And eventually we'll be able to change the way that it looks or something like that, but for now it's a little start at least. I can also do things like judgment holds of has type, empty context, 15 num, and it says yes, whereas if I put in x, then it'll say no. So I've already got a little type checker. And furthermore, I can even put a meta variable in here by writing down the name of a non-terminal, and then I can say, what do I want as the output? And then it'll give me assignments of that. And so we can see that 44 had the type num. let's write a little more. So yeah.
What if you change the mode? So, for example, the expression is the output and the type is the input, and then try to find a number that matches the type.
Then it's actually going to be upset because I put a non-terminal in a context where it would be an output, and so it doesn't know which one to do. So there are facilities for randomly generating terms, and you'll see those in a little bit that match that like fall into this kind of a thing. So you can say like, you know, give me 100 well-typed terms, and it'll definitely do that, assuming that you write your rules the right way. But for this context, that's not going to work. Okay. So another thing we might want to do is the type of a variable. And so the way that we find the type of a variable is we look it up in our context. So I'll say look up gamma x t, then x has type t. And so now we need to define what lookup is. And this has the same mode because it's essentially a function from the context and the variable to the type that we found for it. And then we want to say, well, there's two possibilities. One of them is that we did a lookup on extend some other gamma with x being t, and we looked up x and we found t. So in the pattern matching language of Redex, when you repeat a variable in two different pattern positions, it means not only do those things both have to match the syntactic category given by that name, but they actually have to be the same thing. So when I write my x in both places here, it means these had better be the same x that it found. Like they have to be variables and they have to be the same variable. And the other possibility is, like, let's say we have some other x. Then we are going to look recursively in the rest of the context there. And you can also name rules if you want, like yeah. And then they show up in the figures when you render it. Yeah.
Don't you need to say that they can't be the same?
I do.
Okay.
Yeah. So, and then the way that I'm going to define them being different, I'm just going to copy and paste it for the sake of time, I'm going to copy paste it real quick. Just to avoid typing as much. So there's a notion of meta functions in Redex, which I'm not going to get a lot into tonight just because it's a big system and I don't have time to do everything. But they're essentially functions that live sort of on your meta level rather than on your object level, and you can use those to dispatch on things. In this case, I'm saying the patterns of a meta function match top to bottom rather than allowing you to pick any arbitrary rule. So here I'm saying that if that x and x are not different, but having ruled that case out, then x and y are different. So then what I add is where so here I'm saying where hash t, which is Racket notation for true, is the result of different x and x2. And now I can write down a few more rules. We could say, what else do we have? We have application and lambda. So for lambda, we're going to take the context that we are looking in, extend it with the argument name and the argument type, and then say that the body of the function has type t2. Might as well call this t1. And then we can say has type in gamma, lambda, x in t1, e sub body, arrow t1, t2. And then our final case is application. So for application, we're going to have E1, let's call it eFun and eArg. And that's going to have type T2, just when we can say that eFun has type arrow T1, T sub 2.
Wait, am I misremembering? The language wasn't type, was it? You have type annotations on the lambda parameter in the grammar?
Yeah, I stuck it right here. But it wasn't when I got going. I kind of snuck it in a little quickly. And eArg should be a T1. And now we can do things like check that that lambda x in 45. Oh, that didn't work. What have I done?
Is it because you have an extra T at the end, so you're trying to get the output type of that, or?
So
The inner T should be the empty context.
how so?
Oh, that's there.
I think that all looks okay. But I can say that we want to check that
Maybe different T's at least.
so this is me asking for the thing that it finds for that T.
Yeah, but you served twice, right? So
No. So what have I done? So we've got
Wait, should be uppercase each and no, it should.
this is why I make crib sheets for this kind of thing. So we got that, we got that, we got. Interesting. Well, in the interest of time, let's hop over to my crib sheet here.
What exactly did refers to x2 in the...
That said that any x that occurs in the body of the function refers to the x in the argument. So it means you get substitution and alpha equivalence for free.
Okay.
Actually, okay. What we can try doing is so when I said that I'm going to trace this, it said that no case matched. So that's quite interesting. What if we say arrow num? That works.
This extends judgment that you have, that looks like it has 3 arguments now.
That was the issue. Thank you. So one way that I could catch this is I could say,
Types.
yes. Yeah, I mean you can definitely do this in 12 if you want to do it in 12. That has different trade-offs for what it makes easy and hard. You can also have it insert runtime checks to tell you what you're doing wrong. I know. Yay. Okay, now it finds the type. Yeah. And so let's say I had left that as it was and I'd inserted the contract. Then I actually get something useful, which is to say that it expected something that looked like this, but it got something that looked like this. So actually, it would have helped me catch it had I inserted the contract up here. So now you get to see, like, part of the advantage of live coding in front of a group is you do it wrong, but then the group gets to see how you fix it when it goes wrong and what some of the tools are. So I think that's actually kind of useful.
So it wasn't coded, right?
Oh yeah. Right. And so having defined a type system, the next thing I'd probably want to do is start defining some operational semantics. But in the interest of not keeping you here for hours and hours and hours, I'm going to pop over to the one that I've already made for that demo language that we saw earlier in the slides. So here, we've got this language called CSL for our mini cut-down version of our contract specification language that we use at work. I basically, we were doing this to try to prototype a revision of the language earlier this year. I thought, that's kind of fun, and just kind of ripped out a chunk of it and decided to bring it along tonight. So, right, so we've got our contracts, we've got our expressions. Note here that you can pick, you can give multiple names to the same non-terminal. That just makes them synonymous. So here, when I'm using an expression as a predicate, then I call it P. And sometimes it's more readable to call it expr instead of E, so I also make that as a possibility. You may note that this looks a lot like the slides, and this is because the stuff in the slides was actually generated from this specification right here. If you look at the slide source code, yeah. This is definitely code made for me, but yeah. And we've got Unix epochs for dates and times because I didn't want to put in all the actual dates and times. Right. So then we've got our syntactic notion of values. We've got our agents. We've got our unary operators, binary operators, event types, variable not otherwise mentioned. And this language has only one binding form, which was this thing where we're going to have some event called x, which is going to have type tau, which is a p, which is a payment. And then we say that our predicate p, that refers to x, and also our contract c refers to x. So that's another one of those binding form specifications. And now I can actually, write some examples and test out my grammar. So in this particular case, I can define C0 to be the contract success. This function, or this operator term, is essentially a quotation operator for Redex terms. So if I write term around success, then it rather than trying to evaluate it in Racket as a Racket definition named success and saying there is no such thing, it instead is going to treat it as a thing from my language. And this test match feature is something that comes with Redex, where you give it a language, you give it a pattern with respect to that language, in this case the name of the non-terminal C, and then you give it a value, and when this is run, it will attempt to match the pattern, and it'll throw an exception if it doesn't. And by including this in a submodule called test, I can then say, hey Emacs, run all my tests, or hey DrRacket, run all my tests, whatever it is you want to use. And then it'll test to see if it works, and if it doesn't, it'll crash, and then you can go back and fix things. So it's nice when you're developing this kind of a specification to have some things that keep you honest while you go. And then I might have a loan where I'm going to have a payment from Alice to Bob, and then I'm going to have another payment from Bob to Alice, where Bob is paying Alice 5% more than Alice paid Bob, and where the date of the repayment is 1 month after the initial payment. The comma here is an anti-quotation operator, so that allows me to inject arbitrary stuff from Racket land into Redex land. So here, when I'm injecting month, I'm actually injecting the number of seconds in a month, where we assume that all months are 30 days long. Sorry?
It's finance, right?
It's certainly easier. Yeah. So, and then here I can also test that this fairly complicated expression matched my grammar. Okay, but now we want to evaluate expressions in the language. We want we get this expression, we get this event coming in. We want to, be able to check whether or not it lives up to that predicate, and then continue working. And so here we see the grammar of evaluation context. This was also the thing that was on the slides. But I'll go into a little more detail now that I'm not trying to shock and overwhelm you with how big it looked. Yeah.
Could you maybe explain what you mean by working in this context? So you're seeing an event, and what is it that you expect to be working?
What I meant here is that in this case of a loan, we have a payment coming in, and a payment is the event that can occur here.
Sure.
And then, but that needs to live up to this specification right here. In other words, we need to have the right sender and the right receiver of the money.
For that one payment.
That particular.
It's not checking for the contract completing or anything.
Nope.
Okay.
Yeah. But in order.
So just like if this event occurred, I guess also it's at some point in time, it would match something in the contract.
Yeah. And in order to implement that later, we're going to need to know how to evaluate expressions.
Got it.
Yeah. The full model that I ripped this out of has contract evaluation. I didn't think there'd be time tonight, so you're just getting expression evaluation. But if we have some time at the end, I could show you more.
The only thing you're doing there is just, writing a contract and then testing that it matches the grammar.
In that case, yes. Yeah. But in order to eventually evaluate contracts like this, yeah. So that's a concrete example of the sorts of things I want to be looking at later. Yeah. So the way that these evaluation rules work, a lot of people, I think evaluation contexts are not part of the standard Danish CS curriculum, so I'm going to just give a quick intro to what those are. So oftentimes you'll have evaluation rules that look something like, let's say we've got E1 applied to E2, goes to E3 applied to E2, when E1 goes to E3. Right, so you've got a lot of these rules that aren't really doing much, right? Like all you're doing is kind of zipping around the expression, trying to figure out where the cool stuff happens. And so one way to write these rules down is you can just write down a bunch of sort of bureaucratic rules and then maybe separate them a bit from where people should really focus. Or you can alternatively define a grammar that represents the places where this can happen. So in this context, that grammar, which we'll call E, would have a production that looked like a big E followed by a little e. And also, it's got the hole. And so then we have an operation called plugging the hole inside of the grammar. And so if we want to plug something into the hole, then we would say, essentially what it means is we're gonna find that hole and put the thing in it. So if we want to define that, we could say maybe that we're gonna define E of little e. That's going to be some, if we're defining it, so we'll say then that like EE of this little e, let's call this 2 and E1, is going to be equal to big E applied to E1, E2, and whole with E1 with E put into it is just going to be E. I'll use different parentheses for this one. Right, so essentially we've got an expression and we've figured out where we're going to do some work, and then we've separated that out. Then we can just have the interesting rules like lambda x dot body applied to some value goes to the body with the value substituted for x. Right? And like rules like this are really the thing we usually care the most about. you know, these rules here, they give our evaluation strategy, so that's important, but they're kind of tedious too. So it can be nice to separate them.
What did you call this method?
Evaluation contexts.
Okay.
And so evaluation contexts are also nice if you want to implement a language with control operators, because if you want to have like call CC or shift and reset or something like that in your language, then it becomes very nice to be able to include part of that E inside of one of the big E, the evaluation context, as part of one of your values. Like that's what it really means to capture continuation. And the work on those came out of work on operational semantics for control operators way back in the day. But it turns out just to be a nice technique. And the other nice thing about it is that it allows you to specify multiple evaluation strategies just by picking a different notion of evaluation context. So another thing we might have in this evaluation context is we might have another rule, which is VE. And what this says is that we're only allowed to try to evaluate the argument position of a function application when we've already reduced the function position to an actual value. And by having a grammar for values that doesn't include reducible expressions, then we're in good shape there. So, but whereas if we put EE here, we've now chosen a non-deterministic evaluation strategy where we could have gone either way. And if we really want to evaluate our the arguments to functions first, then we could write our evaluation strategies with a little value right here. And so it's nice that we don't have to go repeat all of our rules for like beta reduction or addition or whatever else it is inside of there. So in this expression language that we've seen so far, the evaluation contexts are either the top, so interesting work is going to be the whole expression, WH whole expression, or, yeah.
So the trick is, like, if you were writing the small step semantics
yeah.
in a normal derivational way, you kind of have to repeat this, which one reduces first for the minus rule or for the plus rule. But
yeah.
Here you only do it once and then you're done.
I mean, you do the same amount of work either way. It's just this way lets you factor out the choose the evaluation strategy part of your rule set from the actually do the reductions part of your rule set.
Okay. Yeah.
But either way, you've got to specify where it is. It's just in the one you can specify it as a grammar, and the other one you specify it as a set of inference rules in your reductions.
Okay.
Yeah, but you don't have to repeat all the things that doesn't change the environment.
Yeah. Yeah, that's right. So I like this style. Yeah. So, you know, we can evaluate under, so what this says is we can evaluate a whole expression. We can evaluate under a unary operator. We can evaluate in the first argument of a binary operator, or if that is already a value, we can evaluate in the second one. And then arguments to payments get evaluated from, or to the payment constructor get evaluated from left to right in all the fields. So we have to reduce all the earlier fields to values before we can start reducing the later fields. And I think that what I should do is show you how the actual reduction rules work, and then we'll take a little break, and then everyone stretch out a bit, and then we can come back to it, because I've got a lot of stuff for you tonight. So the actual reduction rules were written on a much wider screen. We have, but it uses, so in Redex we have this thing called reduction relation. So first we tell it what language we're working in, and that's in this CSL with evaluation. And so CSL with evaluation is a language that has everything CSL has, plus it has this extra non-terminal capital E. And this domain and codomain annotations are ways to get better error messages if I type something in wrong, which is nice. So, you know, in order to operate unary operators, we're going to say that when we're in a hole given by the evaluation context capital E, and we're focusing on minus applied to some number, then we take a step of reduction by escaping to Racket and then using Racket's unary minus. So that's where that comma comes in handy when we're dealing with kind of primitive stuff. And then this last thing here is just an optional name that we can use if we want to take a look at if we want to look at some of the visualization tools eventually. And then if we're in a hole given by E, we see not of some Boolean, then we can use Racket's not using the magic of comma. If we are in a hole E, where we have get agent applied to the payment constructor with all of these things being values, then we can extract the value v agent. And then, there's the same thing for each of the record projection operators where it says how to go from its argument being a value to the actual value that we care about for the whole thing. Binary operators use the same trick where they escape to Racket. The reason for putting term around here is that the meta variables on the right-hand side that were bound on the left will be substituted inside of terms. So whatever number 1 was up here, it becomes number 1 down here inside of term, but not inside of Racket, so to say. And if we want to do equality, we once again escape to Racket, less than, greater than. It's kind of a bit of a boring expression language because it's mostly just a bunch of primitives.
How does the visualization tool deal with escaping to Racket?
Let's take a look. So we could say, for technical reasons, this file only includes the non-GUI parts of Redex,
Okay.
which is why I have to say require Redex here, because up at the top, so there's like a cut down version without because one of the things I'm going to do later would cause that to not work. So we can say traces, right? Oh, what's it called? Traces, yeah. Okay. So we're going to do traces of, what do you want to say?
Add two numbers.
Yeah. Let's do it something a little bit more fun. And then, and then we need to give it the reduction rule, which was reduce extra. Then of course we need to put it in term because otherwise I just give it the number. Okay, so here's what one of the visualizations here looks like. So this is if I actually want to run. So this traces tool is really nice if you want to try to find sources of non-deterministic evaluation in your language. So not required that the arguments be numbers, then or that if say I had not required things to be values in all the places, but instead let them be expressions, then I could maybe get the wrong evaluation order, that sort of thing.
Will that be a split or what?
Yeah.
Okay.
Yeah, this just gives you like a graph up to some predetermined depth, and then if it ran out of the depth, then you can click a button to get more. It's pretty nice. There, nice and big. Yeah. So this is pretty handy when you're trying to figure out your things, and you can also, tell it to use dot or whatever to lay things out. Yeah. Okay. Right. And then in terms of the figures, if we say what's it called?
Like say that it prints a derivation and then kind of as a side remark and adding these two numbers give this result or something.
So if I try to give it a derivation for a particular thing, then it's fine, right? Because then it's just going to call the Racket function and give me back the value inside of the specific derivation. But if I ask it to render my rules, you can see that some of it's pink, and pink stuff is escape Racket code. And the expectation is that if you're going to include this in a paper, then you go and tell Redex what to do instead of the pink part, at the very least.
Yeah.
And there's some ways to instruct to say, make a pink plus, say, meta language plus with brackets around it or whatever it is you're looking for. Does that make sense?
Yeah, it makes sense. So when you write a paper, you don't actually replace all of this comma, like now you're experimenting, I'm developing my DSL, and then I don't really care about how to do plus and minus, I just escape to Racket, but when I write my paper I still have to explain to Redex what to do.
How to typeset it, yeah.
Yeah.
So, and the way that works, I can show you.
By redefining what comma means, or
It's more that here you would pick the name of the operator you want to override the display of. So I might say display minus this way, and then this here is like a little function for rewriting the pink display bit to the new bit. So you essentially give it rewrite rules to new renderings of the stuff. And then it's also nice that I can come into my test and I can say I want to test the fact that applying reduce expr to minus of -1 takes one reduction step to minus of -1. And then I could also, there's a version of this with a apply reduction relation star, which will apply it as many times as it can and then give you back all the results. So the reason there's an extra set of parentheses around here is that the outer one is a list because you might get multiple results back if it's not deterministic. In this case, it was deterministic for this particular argument, at least. Okay, so yeah, one question.
Yeah, it seems like you find a way to define semantic and you can evaluate particular expressions and you can test them.
Yeah.
But can you? Does it also include testing properties,
Yeah.
like not getting stuck?
Yeah. So I've got tests of progress and preservation later in this demo after the break, so you can see what those look like. Yeah.
Sorry.
All right. So I think we should take like is 10 minutes long enough? Do you think, or 15?
10 is okay.
10? Okay. Let's take a break for 10 minutes, or let's reconvene at like 10 past on that clock. Welcome back from the break. Okay. So I've already walked through one type system with you. I'm going to walk through one more even easier type system just for the sake of it, because it'll be important for something else. So if we want to, so we can use this define extended language thing to slap types onto the language. In this case, I add two new productions, capital T for type and capital gamma for contexts, and it looks just the same as it did in the last one that I showed you. And then I've got my different meta function here. And now I can, say what it is to look something up in a context. So to reiterate, when I say mode, then I specify which of the positions in a particular form of judgment are to be treated as things that must be provided, and which of them should be things that Redex can determine by applying rules. So in this case, the types should be able to be determined by looking at the context and the expression. I'm not saying uniquely determined. Like, it doesn't have to be a function, but at least it's going to be like able to generate them and find them. So when I have my first rule for looking at something in a context, then we see that it's a context that ends with x being a t, and we're looking for x, then we found t. And when we've got some y with some type y, and we're looking for x, then we can do that by looking onward as long as x and y are different. Okay, and then I generally like to make type systems with in a sort of a bidirectional style where I write down first off what it means for one type to be compatible with another, and then kind of plumb that through. What you're seeing here is a little bit of a vestigial bit of that, where I've defined what it means for two types to be the same. Right now they're just syntactic equality, but if I wanted to, I could use this to attach some subtyping or something. Right, so bool and bool are the same type, num and num are the same type, agent and agent are the same type, and then any payment type is the same as itself. Okay, so when I want to look for the type of an expression, then I can, if it's a variable, I look it up in my context. If it's a literal Boolean, then, that's just got the type bool. The reason this is crossed out is because I don't refer to this meta variable anywhere else in my context. Like I've matched that it's a Boolean, but I don't use it as part of my output. Yeah, same for a little number or a little agent. A payment constructor, it's got an agent, it's got for both the agent and the recipient, and then it's got numbers for both the amount and the date. I'm going to kind of scroll through these because I don't think that they're all that interesting, to be honest. Does anybody want me to go more slowly? Okay. Okay. So I've given a long list of rules, and like that, maybe they're right, maybe they're wrong. So one thing that I might want is a version which just has inputs. So for that, I can say that if to check a type E against T, I can, determine its type and then check that it's the one that we were looking for. So far, so good. But, if I got my type system right and I got my operational semantics right, or if they agree with each other, then it should be the case that taking a step of evaluation, it should be the case that any well-typed expression is either a value or it can take a step of evaluation. In other words, nothing got stuck. If I'm doing what I learned to do in school, then I sit down and I prove this. If I'm busy, then I might want to first randomly check this. So Redex has a nice feature where I can just randomly generate 100 well-typed terms and then see if it's the case that this property progress holds for each of them. In other words, that something is either that a well-typed term is either a value or it can take a step, right? So just getting into this, we've got a term coming in, and a well-typed closed term, I should say, which is to say there's no free variables in it. So, if it's got some type T in the empty context, then if it's well-typed, then either it matches the syntactic category V of values, so that was this one right here, or I can apply my reductions and I get back a non-empty list of results. In other words, it was able to compute at least one further step. And in this particular language, because I've engineered it to be deterministic, it will always compute exactly one step. But this is a nice general formulation where we just say it's non-empty. Okay. And so what I can say then is I can call redex check in this CSL with types language. And then I can say that I'm going to check things that are satisfying this particular judgment. So in other words, I'm going to find E's and T's such that E has type T in the empty context. And then I'm going to check that progress holds for that particular E. So of course I've written a thing for which that actually works. So it's off thinking about it, but you can see the results of some previous ones before. So this is one where it tried 943 times, and then 57 of those times the random seed it started with its generation strategy, it didn't end up actually finding a term, so it threw those out. So that's why it's not 1,000 here. But out of those 1,000, 57 random seeds the generation failed, and 943 of them it held. Progress held. So let's make progress not hold. So we're going to go up to reduce expr, and let's just comment this case out. So I'm going to run my tests, and we found a counterexample to this statement, of progress, which is quite nice, right? So we ended up with a well-typed term or false true, and because I had commented out my reduction step for or, that can't take a step, but it also doesn't conform to the grammar of values because the grammar of values, like true and false are the Boolean values. So that's pretty convenient. Like other kinds of sort of quick check inspired systems, it gives us actual counterexamples, and that can be much handier than like, why won't my proof go through? So even if you plan to prove it, testing it is nice. Yeah.
How do you ensure that it generates some interesting expressions?
Yeah, so there's a collection of things that you can use in Redex to check for like the coverage of the different relations and get it to tell you which of the rules that it's used while generating. I don't want to get into all the details of that right now, but We can do a little bit. It's not looking at my local docs.
If you want to go on the internet, it's statistic.
All right, I've got a local copy too. Right. So there's a whole bunch of stuff here where we can tell it like what do we want to compute coverage of, and then we're gonna try applying it, and it'll figure out how much I've done each of the things. So yeah, and then okay. So another thing that we might want to be true in order to get you can do type safety without progress and preservation, but if you can do it that way, then it's very nice. So. So the other thing we might want to have is preservation, which is to say that if we have a well-typed expression and it takes a step of evaluation, then it's still got the same type. This is true for many languages we care about. It's also not true for other languages we care about, but in this case, it's true. So what this says is that this is true for open terms. So we need to have the context in which that term is well-typed. So we have a gamma and we have an e. And so the first thing that we do is we extract all of the types T that this expression E could have in gamma. So this judgment holds is going to give me back a list of assignments of T, and then we're going to iterate over all of those. This for/and operator in Racket basically is like in Haskell if you just say like and of a list comprehension. So in other words, we're going to be taking each of these types and calling it type locally, and then computing a Boolean for the body of this thing, and then we're going to AND all those together to get the final result. And then if we want to see what steps it can take, right? So we found all the types it can have. Then we're going to see all the steps it can take. So we want to, we're going to apply our reduction relation once and take a step for this expression E, and then we'll get back this thing called stepped. And then we're going to check that in the original context, the step still has the type. So in other words, yeah, every potential type we can assign and every step we're going to take, we're going to say like, it still keeps it. In practice, there's only going to be one type and there's only going to be one step, but this is a nice general way to write it that I can copy paste to other developments if I want to. And so let's go try to break preservation. So the way I might break preservation is I might come up here and say that or is going to have the type number instead. Okay. Run my tests. My CPU graph, if we looked at it, is kind of up a little bit. I forget if there's a way to make it run on multiple cores at once. It's not doing it right now, which is unfortunate. Because this is a very easily parallelizable problem.
I think there are only 2 cores in the machine, right? So
It would be nice to use 2.
only twice as fast.
Okay. So in this case, we found a counterexample by changing the type given by or to say that it must have been a number. And here we found in a context where U is a Boolean, J is an agent, Z is a payment, then blah, 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 blah. Yeah. It found a sort of a large counterexample this time.
Doesn't it do any minimization?
It might. It certainly isn't doing it right now.
I think you need at least a couple of things to make a counterexample that contains all. You need at least an expression that contains something that's a number that shouldn't be a number. So it's fairly shrunk.
I think minus of or true false would have been fine though.
Yes, true.
Yeah. Okay.
Well, it's preservation, so we just had an or, which was typed as num, and evaluated, and got a bool back, then that would be a counterexample. So I think that's a really good example. Doesn't really get much more.
Yeah. That's right. Yeah, so if or true true were typed as number, and I took a step evaluation to true, then true does not have type number, so it would be wrong. So there might be a way to get it to do minimization. I don't actually know off the top of my head. Okay. Right. So now we want to talk about, contracts being well formed. So this is a set of rules that we saw before. So the only kinds of contracts we have in this cut down version of the language are the ones you've seen here. Like we don't have any functions that return contracts. So the entire thing is fairly simple, right? So we essentially take all of the productions of the grammar and say is contract on them, except for the one that binds a variable. And in that case, we do it we have some expression typing in an extended context. Yeah. And so that's the end of this specific collection of stuff to go through. I think that everyone's brain is probably getting pretty full at this point, so I don't necessarily want to do a lot more, but if you want to play risky and do a bit of live hacking, if you're curious about something, then I think we should do it. Are there anyone who wants to poke at stuff?
I mean, I don't want to do it. I want to see you do it.
Yeah, but in what way should I poke at it? Okay, so actually, let's change gears. Okay, so I've gone and I've written down a notation for contracts with a lot of parentheses and a lot of sort of keywords, and now I'm returning to my recycling metaphor, and now I've written it down but I need to go implement my language, right? Because I need to put it in front of some actual users and see if they can figure out this thing that I'm so proud of. Well, most people I'd want to put it in front of have not sort of drunk deeply from the spring of Lisp and are not going to think that a heavily parenthetical notation is particularly friendly. They're probably not going to want to sit down and write test cases in an Emacs buffer, right? They're going to want something a little bit more high level. So that means that I need to, go out and actually implement my language. But that's a lot of work, right? So at OPLSS some years ago, David Van Horn showed me a way to hook a Redex model up to DrRacket, which is the standard Racket IDE, and then use all of its features for free. And this is not something that, as far as I know, is endorsed by the Redex team, but it seems to work pretty well. So, I'll show you the result, and then I'll show you how I did it. So, what did I call it? Right, so here I've got 3 contracts. Let me see if I can. Can you read it in the back? Okay. So here I've got sort of 3 contracts written in my notation, but note that they're not actually parenthetical, right? I've got infix operators. They've got some precedence going on. If I put the mouse over P2, then it points back to its binding site, or if I put it over P, I get to see that. I can right click on P and I can say oh, let's rename it. I'm going to call it payment, and then it sort of alpha converted my thing. This is all pretty nice, and when I sat down to do it for our little prototype internally at work a few months ago, I think I spent a half a day on getting it to work. So, I can click run here, and it just pretty prints them. But let's say I've got a type error. What if I replaced and with plus? I didn't like that. Why is that? That's.
It's because plus should be between the equality sign instead, right? Or
I'm trying to write something wrong here, and I think it's because I got my operator precedence a little bit under constrained. So let me just make it wrong in a different way. Let's say where this is a plus. Okay, and then I can click run. I say, oh, okay. Right, because what I want, right.
That's some C++.
I worked super hard on this error message. I spent 10 minutes on it. Okay, so what it's actually doing is so remember, we basically get a type checker for free by writing down our type system in Redex with the right modes on things. So what I did is I said that like, well, when there's a type error in my language, in my IDE here, then what I want you to do is actually like dump a trace of how you step through all the typing rules and where you get stuck. So actually what happens is I want to check that this is a contract, this whole thing. And so we say, okay, so the first thing we're gonna do is we're gonna check that this payment.agent equals Alice has some type in this extended context. This little 8 in brackets here is coming from the binding form specification I gave in Redex. It actually goes through and uniqueifies all bound variable names in order to make alpha equivalents be free, basically. And so, okay, so to check that get agent of payment is equal to Alice, to check that that's well typed, okay, well I'm gonna check recursively that get agent of the payment has some type, and then I'm gonna go in and and eventually I find out that payment has type pay. That's great. And then we can see that it's so the greater than sign is when I'm sort of going further in, and the less than sign is when I've come back with some value from my type checker, or from my search over my typing rules. And then if I kind of scroll down to the bottom, I can get back to like where the thing starts not finding any potential derivations. And that happens here, where I want to check that, what do I want to check here? Yeah. You can work it out. Like so this is the kind of thing that is not very useful to give to an end user, but it is useful to like give a potential test user the red underline over on the left. And then you can see what they did and then maybe figure out what's going on. And it's also nice when you want to debug your type system. But yeah, like I said, like you get this for free. Like don't expect super good error messages. Okay. So we'll put that back to equal. Okay. So what else can we do? That's basically all we can do. But how do we do this? So the first step is to write a parser, right? Because you're never going to be able to get from concrete syntax to abstract syntax without putting in a little bit of work. So the first step of writing a parser here is going to be a lexer. This is just using the parser generator stuff that comes with Racket. Yeah, it was pretty easy. So, I define a collection of tokens, right? So what are my tokens? I've got numbers, I got variables, I got agents, literals, I've got negation, arithmetic operators, less than, greater than, true, false, and, or, period, some contract literal stuff, colon, left parenthesis, right parenthesis, these names, curly braces, equality, comma, base types, and end of file. And then I've got just because I like getting reasonable error messages out of my lexer, I've got a little thing to say like, when I want to say, oh, I expected whatever token, then I want to be, or out of my parser, I want to be able to say, I expected a record projection or whatever. This is just a quick little hack to describe them. And then I do the usual lexer trick where you have a function from a string to a token, which takes all your keywords and maps them to the appropriate token and then turns everything else into a variable. And that's to sort of prevent the problem with like stripping off the name of a keyword that happens to be at the beginning of a variable. It's like if you made a variable, I don't know, let's call it theny. Then you'd get the keyword then followed by a variable name ny. That would be no good. So this is a nice way to avoid that. And then my lexer, it just consists of some regular expressions followed by things that construct the actual tokens. Plus here means one or more in this case, rather than the actual literal plus. So this is a fairly bog standard lexer written in Racket. The whole thing is like 126 lines of code, including some tests. So then I write a parser, and this is using a sort of standard LALR parser generator. Do you pronounce it Lalor?
No.
Oh, I kind of wish we did. Lalor. Okay. Right, and so this is so here's here's the definition of the parser. So we give it a collection of options, like it should track source positions, it should use the tokens from this token set CSL that I defined in my Lexer file. In case of parser errors, it should invoke this function right here, which is going to raise a syntax error exception that I defined. And it brings along some extra information so that I can catch the syntax error and report it how I want. I specify precedence and associativity of various operators right here. Then I've got my grammar. The right-hand sides of these grammar productions are a little bit complicated because I'm careful to plumb source positions through them. If I weren't doing that, then it would just look like quotes. Like I could just use Redex's term operator to construct the terms directly. I just believe in source positions. Part for that reason, and partly because I'm going to need them in order to get the rename identifier stuff to work. So, yeah, so I kind of walk through here, and then just, like expression plus expression, gives me my plus applied to the expression and the other expression. Any questions on the parser? I know you're not going to learn how to write this by watching this, but the documentation is quite reasonable, and there's some examples you can read. Okay, so I've write my big parser. Then I've got some various little bits, and I'm happy to send you copies of this stuff. Or you can get it from David Van Horn probably. I believe he's got an example up on GitHub. Okay, and then one thing that's kind of fun that I can do with this is I can actually define a Racket macro that invokes this parser on a string literal in my Racket source code, and then requires that to actually parse. So here I defined a Racket macro called CSL string, where I can, where what that does is it takes in, this is a Racket macro, it takes in a piece of syntax, it matches that against this pattern CSL string, which has to be a string literal, which is what the colon string bit means. And then it invokes my parser on the contents of the string, and it then returns my Redex term applied to that. So if I call CSL string on here, then we can see that what we get out is a little bit of code that would work for my Redex model. So I can write concrete syntax and then use it with Redex in a string if I want to. And what's even more fun, I think, is like, let's say I spell success wrong. Then I actually get an error message right there. And we see that it says CSL parser, unexpected keyword, then. So that's a nice little trick. Hen is also wrong.
The C.
I know.
And
Okay.
then that's because success with 3 C's is otherwise not mentioned.
Right, it's a variable. Yeah, that's right. And contracts don't get to start with variables. Okay. Yeah, and like this one here is just because I was making sure that prefix minus and infix minus played nicely together, and so this is a little leftover for that. But I can do the same thing for CSL expressions. Racket is fun. Okay, so I've got a parser and I've got a lexer. I'm also going to need a pretty printer. So this looks like the usual kind of pretty printer. One thing that you want to be true about a pretty printer is that a pretty printer and a parser should be suitably mutually inverse, in that if I pretty print and then parse, I should get back the same expression, not necessarily the other way around. Right, so at the bottom of my pretty printer, I can actually use Redex to generate arbitrary expressions, and then I can, convert them to a string and then parse them. And the pretty printer library that I grabbed off the Racket package server would occasionally explode, so I just said, like, only run it for 1 second, and if it takes longer than that, then give up on this example. This is what happens when you're, developing things late at night. Okay, so then I can also then I have the same thing for contracts. So this was actually very, very useful when I was trying to debug the pretty printer and the parser, because I could just generate arbitrary nice terms and then check that they're mutually inverse, and the entire thing for those tests is like 20 lines each. And that's really nice to have access to those features of Redex. So that is maybe an example of how having a Redex model available can help you test things for real. I think that Sriram Krishnamurti's group did a Redex model of JavaScript that they tested against real JavaScript implementations. This is me thinking off memory. I should have looked that up before I came in. But it's a pretty powerful thing to be able to do to make sure that your model of operational semantics, if you're trying to model an existing language, actually matches what implementations of the language really do. Okay. So then the next step is the one that is going to be somewhat less satisfying. Now we're getting into a bit of fairly complicated Racket code that I will sort of explain at a high level. I'll answer any questions, but there's going to be more here than you can learn in an evening. I'm sorry, but I think it's still nice for you to see like the order of magnitude of effort that's involved in doing the glue code, right? Because we have our Redex model, we have our parser and our pretty printer. We need to glue those together so that first off, I can say this #lang line at the top and say that I'm going to be, the language this file is written in is this csl.racket. And then following that, it also needs to be able to do things like the syntax highlighting and dumping the error messages when I click run, and how do I handle what happens when somebody types something over at the REPL here, all that stuff. So the way that glue looks is that a language in Racket consists of a Racket module that exports certain names. And so here, that's what I'm doing is I'm exporting the names that matter here. So module #% in Racket means like essentially here there be dragons, or this is some magic. So behind the scenes, like what looks like function application in the surface syntax is actually an invocation of the operator #%app. And having these things be named operators means that they become an extension point where you can override them in your own languages. Because not every language you want to build on top of Racket will necessarily have a fresh syntax. You might just reuse Racket's concrete syntax, but then maybe instead of calling something define, you might want to call it let it be so. So module begin is the name of the operator that's implicitly wrapped around the body of a module. So by providing my own module begin, I can say that this sequence of declarations or this sequence of contracts, instead of trying to evaluate them as Racket expressions, type check them and then either dump the result or just pretty print them in Racket. Top #top interaction is the name of what happens when you type something at the REPL. It'll put that around, and then by defining what top interaction means for your language, you can say what happens when I type something in at the REPL. Read, syntax, and read are the names of the parser, essentially. So that's the R in REPL is read, eval, print loop. In Racket, it's actually like a read, macro, expand, eval, print loop. And so, yeah. And read syntax is the version of read that tracks source locations and things like that. Get info is the thing I'm going to export from my... If I export a function called getInfo from my language, then DrRacket will query getInfo to find out how to do things like syntax highlighting and indentation and all those sorts of user interface things. And then this read1CSL is something that just invokes the parser on a prefix of the input rather than saying the whole input has to parse at once. And that's going to be used later on for other things. Okay. So first I'm going to import my parser and my lexer. And I'm going to import my pretty printer, but I'm going to say like all the names that come in with it should have p : appended to the front because there's names in the pretty printer that conflict with names in other parts that I want to use. I'm also going to require demo, and I'm going to require it for syntax as well. In Racket, there's a separation of bindings for different phases, which is to say that the bindings available in a runtime program are distinct from the bindings that are available in a compile-time metaprogram that could give rise to that runtime program. And those are distinct from the bindings available in a compile-time metaprogram that can generate a compile-time metaprogram that can generate your program, and so on and so forth until you give up. And this allows it to have a nice sort of compilation model and get like separately compilable modules and things like that, as opposed to other metaprogrammable Lispy languages where the semantics of things like that have historically been much less clear. And then this operator define for syntax is a version of define that defines a thing one phase earlier. And because I need some things repeated for compile time and runtime, because I need to type check things at compile time in order to have them get the red squiggles in the editor, but I need to type check them at runtime in order to have them work in the REPL. I just want to define all that stuff in both phases. And so I could have defined that in one module and imported it to both phases, but I just defined a little Racket macro that just duplicates the thing because it's good enough for here. Okay. So the first thing my language is going to need to be able to do is to do static checks, which is to say, type check it. So I pull in a contract. I strip out all the source location information because Redex doesn't understand that. And I then match it against the syntactic categories of contracts using this Redex match operator that we saw earlier. If Redex match didn't match, then I'm going to throw an exception. Raise syntax error throws an exception that Racket knows how to use to like highlight some source locations, which is why I passed the original contract syntax in here. If it returned more than one thing, then I'm going to say it was ambiguous syntax. This should never happen, but there might be a bug in my parser, so who knows. Or rather a bug in the specification of the language, I should say, because this is at the abstract syntax level. And then I check whether the contract is well formed in the empty context. And if it is, then I'm going to return a bit of Racket syntax, right? So this is going to be something that kind of lives at the next syntactic phase, and it's going to be that CSL operator, which is like the version of term that specified the language applied to the contract syntax that I wrote. And if it failed to be well formed, I then turn on tracing for all of my forms of judgment in my language, and then I rerun the type check, and then as a side effect, that dumps out that little trace that you saw over in the REPL earlier. So this is all a lot of duct tape, but it's convenient duct tape. And then I throw my exception after dumping that out. So the next thing I need to be able to do is to get the rename identifiers thing to work. There is a way in Racket to track all of the binding forms and the source code as you go through things, but there's actually like a dumber thing that works just fine, which is to arrange to emit a Racket program that does nothing but has the binding structure and source locations that you care about. And so I wrote a macro called lexical because it deals with all the lexical stuff that takes a bit of syntax in and arranges to emit a Racket program with its binding forms and its source locations. So one binding form is this thing that receives an event. And so I'm just going to like bind that name to void, which is the Racket name for the unit type. So to the constructor of that. And then the body of the let is just going to be lexical applied to the expression and to the contract. If it's an identifier, if it's a valid identifier in my language, then I just emit it. Otherwise, I emit a trivial program that does nothing, so unit. If it's a sequence of things, then I just recur down into that and apply lexical to all of them. And if it's anything else, then I emit nothing. And this is enough to cover the whole thing and generate a Racket program with the right source locations and binding forms such that when I mouse over a thing, the little arrow will point at it and all of that. So it's a hack, but it's an easy hack. Then I define what happens in the REPL. Well, first I call static check on the thing that was written, and I then pretty print the result to the current output port. And my notion of module begin. So this is to say when I'm provided with all of the declarations that the user wrote in DrRacket, first I invoke static check on it, on each one of them. And if all of those succeed, right, because that'll throw an exception if it didn't. So if all of those succeed, I then emit a reference to Racket's module begin, surrounded by, and inside of Racket's notion of module begin, I then import my Redex model. I have a little thing here which is part of how to set up the parser to be used at the REPL. I then emit lexical of E for all of the E's that I had. Probably that should be C for contract. And then I pretty print each one of them. Right? So the dots here, like the ellipsis matches the ellipses up in my pattern right here. And so whenever I have an E ... in my pattern, then any E's that occur in my output have to be underneath the same number of ellipses, and then the thing around them will be essentially copy-pasted the right number of times to make it work out. So because I have an E here and an ellipsis here, that means I'm going to be pretty printing every single one of my E's. Then I've got a way to invoke my parser and a way to, all of this is just glue code that invokes the parser that I wrote and then ensures that the resulting data is suitable for things. The key thing to remember here is this strip context, because Racket syntax objects, in order to implement hygienic macros, have more than just source locations on them. They also have information about where they came from in the program. And if you just parsed a thing, you don't want it to have any of that by accident, and leak guts of the variable scopes from the implementation of the parser. So calling strip context makes that go away. And then finally, I've got my get info. So my get info, so get info is given a bunch of information, and then I'm supposed to return a function that DrRacket will then query to figure out how to configure itself. And it asks for a key and then a default value. It gives me a default value to return when I don't have any fresh thing to say here. And then if it asks for a lexer, then excuse me, my throat's getting dry. So if it asks for a lexer, then I call my CSL lexer and then return the way that DrRacket should highlight that. So if you look at the docs for DrRacket, it says, I've got these highlighting categories: keyword, constant, parenthesis, etc. And then you return a collection of the token, its category, what kind of parentheses it should match. So I didn't configure that for this language for the sake of having it small. And then also the location of it in the file. And then otherwise, I'm not going to respond. And so that's 145 lines of fairly dense racketeering, but most of it is reusable to other language models. If you iterate on your Redex model, this doesn't have to change very much. You'll have to tweak your parser as you go, but this glue code stays fairly constant. You might need to add or remove a particular token from this table, but you can kind of muddle through it. If you're able to write it once or get it from someone who has written it, then you don't have to be a major Racket expert to do this kind of thing. Although it helps to know one who you can ask questions to. The mailing list is usually a pretty good place. Okay. So returning to my slides, we've exited from the feeling of stress and being overwhelmed. We've used some actual tools to achieve the clear white light of understanding, and now we're done. So some things that I didn't talk to that you can do is I didn't really get into the random testing very much. You saw a little bit of it. I didn't show you at all how to check for coverage, but you can definitely do that. You actually saw a little bit of how to visualize reduction relations. I didn't plan to do that, but I ended up doing it. And you've seen that you can control typesetting, but not the nitty-gritty details of it. But you can do all those things, So just to what you should remember is Redex is a DSL for language design. You can use it to sort of quickly get a slow implementation with bad error messages, which is often what you need for testing purposes. And then if you write a lexer and a parser, then you get an IDE almost for free that lets you do most of the things you care about. Happy to answer any questions, and then then we're done.
Can we give a round of applause?
So anybody has some questions?
Yeah.
So how would this approach compare to other approaches to prototyping a DSL? I'm thinking, there are language workbenches out there like IntelliJ NPS or stuff like that. We have sort of, are you in a position where you can sort of contrast and compare, or?
Yeah. So the question is, how does this compare to other ways of doing of prototyping a DSL, and in particular there's things like IntelliJ NPS. I haven't used NPS. I have done a lot of quick and dirty things in Haskell, where you sort of essentially like write down a data type and some functions and hack through that. I've seen Mod and a few others. So the specific niche where Redex is pretty good is where you want to be writing down things kind of in rule form. Like, I don't think you get a good IDE out of this. From what I've read about NPS, I think you'll get a much better one out of that. What I think you get out of this is it's fairly close to the notations used by practicing programming language authors, or by practicing programming language researchers, I should say. And there's a lot of tools that sort of fit that niche pretty well. As compared to something like OT, the typesetting, I think, is more painful than with OT, but you get all of the reduction rule testing and type checkers and that sort of thing, which you wouldn't get out of OT. On the other hand, OT can generate you a skeleton for implementations, I think, in OCaml and Coq and maybe something else. And this won't give you that. Yeah, that's what I got for you.
I remember I was at a talk actually with you, Jesper, at Isolat.
K framework?
Yeah, exactly. And there was someone presenting the K framework. I think, I don't remember his name, but it tried to do something similar, but it was a lot more complicated. I did not understand very much, to be honest. Do you know about that?
I know about it, but I haven't ever used it for anything. Yeah.
But it was definitely trying to achieve something similar, but
Yeah.
also more.
One
Didn't
way
they do
that-
an implementation of one like a real language, like Java or something. No, Ethereum.
Ethereum is formalized in K, I think, and the reference implementation is in K.
Right, cool.
For the EVM, yeah. But I don't know how it works.
Some very complicated XML syntax. And also, you don't give an operational semantics in a traditional small big step style, but these other formats.
It's like a pattern matching term rewriting style.
Yeah.
So for what I understand, you get a little IDE and then it's an interpreter that runs in this IDE. And but can you do side effects? Can you do I/O? Can you do something with files or network or
like with Redex?
Yeah, I mean, is it only for pure languages that you are playing with, or
so
how far can you go with the language that you are experimenting with?
So you can escape to Racket whenever you want,
Yeah.
with the comma. So you could absolutely add side effects if you wanted.
Okay.
Should we try it? Let's add side effects. Okay. Right. So let's say we want to come back to
launch missiles.
Yes. Okay, so we're going to come back to our lambda calculus, and we're going to add an operator called launch missiles of E. And then we're going to come down to a type. What's the type of launching the missiles?
Doesn't matter. Could you go, I don't know, something's Boolean.
Is it a number?
Number of
Yes,
deaths.
it's a number.
How many missiles?
Okay, why not? Let's
the type of E, right?
I was gonna say the E was a number of how many missiles to launch, but
Just launch some, and then you could talk afterwards. I mean,
okay. So E is the number of missiles that we want to launch, and then it's gonna return the number that were actually launched.
Yeah, zero. Please, no, make a new primitive type called new or something.
Okay, so now we need some operational semantics. So we'll say, actually, you know what? I'm gonna add this to my little CSL instead. Okay, so we will have, just because this one already has operational semantics, so I don't have to hack them up from scratch.
So repay the loan or fire the missiles. Well, the contract is either you pay me or I launch the missiles.
Oh yeah, I can just add it to my unary operators. Okay, so unary operators will now include launch missiles, and
So this is my contract.
then now we need to go into our evaluation place, and we need to be able to evaluate the number of missiles to launch. Oh, we already got that already because that's a unary operator. Awesome.
It's mostly used in contracts about protection money.
Okay. So now we'll say then when we're in a hole of evaluation context E, and we have launch missiles of
Should be Asian, shouldn't it?
what's that?
Should be Captain Asian.
Let's not bike shed the nuclear war. Okay. And then actually we're going to say that the result of launching missiles, like this is just going to destroy the surrounding program, so we're not going to be in the hole anymore.
So it's failure.
It's going to be number, and we'll call this war, and then okay, this should be sufficient. Let's try running it. We'll say apply reduction relation star reduce expr of term.
This isn't how you're supposed to define effectful semantics in Redex, is it?
I mean, I thought they were asking whether we could have side effects in our model that for people to play with. But yeah, no, like normally, like I would, if I wanted, let's to like actually do it, then I would do some sort of a system where I kept track of like the content, the world in which the effects were happening, depending on what's going on. You know, like do like you could do like a CSK machine, or have like an explicit store, or all that stuff is totally doable. But this is fun. I failed. What have I done?
We didn't add. No, you didn't add it to a number, right?
Oh, that's right.
So it's just launch missiles without full.
So the missiles were launched, and then the plus 17 was obliterated. And this whole like playing with evaluation contexts and is how you implement like control operators and those sorts of things. So we actually did have an effect here, which was that it's like an escape continuation kind of thing.
Okay, can I see that effect again? How it's defined?
No. So this is horrible. Like this is an ugly hack, right? So if we wanted to actually like do this the right way, then we might have a model where we kept track of how many missiles had been launched, and then we'd be, moving our, like, evaluating our program with respect to a given, like, missile launch context, where we would then take a step where we updated that context to something where the number of missiles launched so far was incremented. But you can also, if it suits you, you can escape and do real side effects as part of your evaluation. Which I guess is one way where this is very different than the more mathematically minded, pure modeling frameworks. Was that the kind of answer you're looking for?
Yes.
Okay. And you had a hand up.
Yes. returning to your recycling metaphor.
Yeah.
Okay, so let's say that you're doing a lot of DSL and they're not exactly similar, but they have similar features.
Yeah.
Let's say. And so, how much of all of this extra work? Of course, if you change the syntax, you write a new class.
Yeah.
Right. But for instance, this extra work of integrating your DSL in the DrRacket IDE, do you have to redo most of that work, or can you sort of reuse most of what you did?
Mm-hmm. So the question is, let's say, I'm repeating questions just because this is being recorded.
Yeah.
So the question is that if we, let's say we make another DSL or a related DSL in a family or a new version of it, how much of this integration work with DrRacket can we reuse, and how much of it do we have to create again? So first off, we would have to import different files here. So that line would change, but only to the extent that I'm importing different stuff. That's the same. I'd have to define how to statically check something. So, and that's going to vary a lot from language to language. So lines 28 through 42 would be different. Lines 44 through 58, this thing which creates something with the same binding structure, that would be different because the binding structure would be different. I couldn't figure out how to reflect on the binding form specifiers in Redex to get this for free. There might be a way to do it though. I didn't spend a ton of time looking at it. So that one might be able to be made generalizable to the extent that Redex's binding forms feature supports the binding structure of the language you're implementing, which it does for fairly simple languages and not for really complicated languages. This top interaction thing would be, like the contents of static check would be different, and you might call a different pretty printer, but the basic structure looks the same. With the exception of having a different import and calling a different pretty printer, this module begin macro would be about the same. This reader, if you swap out this parser, it would be the same, so I could have made this a higher order function that took the parser as an argument. Likewise for this one.
And most of it you can make higher order functions that also just take the names of the modules and so on.
Yeah, so probably what I would do is I would, if I was doing a lot of these, I would probably define a Racket language for defining Racket languages for Redex models of languages. And in this context, I would then say at the top I'd write #lang, Redex DrRacket glue, and then I would define things with certain names, and then it would arrange to put them in the right spots. And then I'd still have to define the things, but it would be fairly clear what to do, I think. So it's
DrRacket integration DSL.
Yeah, I mean there are a few of those already, but this would be yet another one. So I mean if we look at it right now, this thing where it says #lang reader CSL.Racket, that right there is already such a thing, such a language, because normally you have to give it the thing after #lang has to be the name of an installed package, which has to provide a reader module. But I didn't want to install my demo here as a package because that's a whole thing to go through. But there's a package installed called reader, which reads a string and then uses that as a file name and then takes that as if it were installed and then runs with it. So it's like a proxy that redirects it. So there's a lot of the ecosystem that you can read about. Any further questions? Okay. Thank you all for coming. I really appreciate you spending the evening with me here. And I'll see you around.
Yeah.